Hello friends, we are discussing about 2D transformation. In previous video I explained two-dimensional translation, two-dimensional rotations. Now we study two-dimensional scaling. Scaling means expanding and condensing. To alter the size of an object, we apply a scaling transformation. Okay, to alter the size, okay, maybe enlarge the size, maybe reduce the size. Okay, that is called what? Scaling transformation. A simple two-dimensional scaling operation is performed by multiplying object positions s, y by scaling factors sx and sy to produce the transformed coordinates x dash, y dash. Okay, how you expand or condense? Okay, how you find the new x and y values? By multiplying object positions, that xy positions of that object by scaling factors, that is xx and sy. Okay, that produce what? Transform coordinates. Okay, x dash is equal to x dot sx and y dash is equal to y dot sy. Okay, the scaling factor sx. Okay, if you give 2 means what? It doubles in the x direction, it increases double. If you give half, it reduces to half. Okay, so in the x direction. If you give sy 2, okay, it increases doubles in height. If you give half, it condenses to half. The two-dimensional scaling equations can also be written in the following matrix form. In matrix form, how you write the scaling equation? X dash y dash is equal to sx 0 0 sy x y. Okay, if you multiply, you get new position. Okay. Okay, expand or condense by x direction, that is xx. Sy is what? Expand or condense by y direction. Okay, if you want to double the size of that object, you have to give sx2 and sy2 in both x and y direction. If you give half, if you give only sx half, then only in the x direction it reduces. Okay, if you give sy half, in y direction it reduces. Okay, if you multiply, you get new point value. Okay, new position of that object. Okay, what is S? So S is the 2 into 2 scaling matrix. Okay, next, any positive values can be assigned to the scaling factors sx and sy. Okay, if you give positive value, it increase, enlarge. Values less than 1 reduce the size of the object. If you give sx and sy less than 1, okay, then it is reduce the size. Values greater than 1 produce enlargement. If it is more than 1, enlargement. Okay, if you give sx more than 1, it enlarge in x direction. If you give sy value more than 1, it enlarge in y direction. Specifying a value of 1 for both sx and sy leaves the size of the object unchanged. If sx equal to 1 and sy is equal to 1, then the object remains same. The size of the object remains same. When sx and sy are assigned the same value, a uniform scaling is produced, which maintains relative object proportion. Okay, if sx and sy are assigned the same value, okay, a uniform scaling. If, for example, sx and sy both are 2, okay, uniform scaling means in x direction also enlarging, in y direction also enlarging. Okay, if sx equal to half, sy is equal to half, okay, it reduces the size. Okay, in equal in both x and y direction. Unequal values for sx and sy result in different scale, that is often used in design applications. Okay, if you give unequal size, okay, if sx is equal to 2, sy is equal to half, then in x direction it expand. Okay, in y direction it reduces the size. In some systems, negative values can also be specified for scaling parameters. This not only resizes the object, it reflects it about one or more of the coordinates axis. If you give negative values, okay, it reduces the size. Okay, it reflects. Figure below illustrates scaling of line by assigning the values 0.5 to both x and sx and sy. Okay, so this is the x, this is the line. Okay, if you assign 0.5 to both sx and sy, okay, in both direction sx and sy, it get reduced. Okay, so from here to here x direction it reduced to half, it displays here. In y direction also. Okay, this is the original line. After scaling to half, then it reduces here. Okay, in previously it was here. Okay, then it comes here, and in x direction also it changed, in y direction. Okay, it also decreases here. We can control the location of a scaled object by choosing a position called the fixed point, that is to remain unchanged after scaling transformation. Okay, we can control the location of scaled object. We can control the location also. Okay, that is called fixed point. It will not change the point. Okay, to remain unchanged after scaling transformation, we can mention the fixed point. Coordinates for the fixed point xf, yf are often chosen at some object position, such as its centroid, but any other special position can be selected. Okay, so coordinates for the fixed position. Okay, if you don't want to change the position, okay, for fixed point xf and yf are often chosen at some object position, such as its centroid, but any other special position can be selected. Okay, we'll take an example. It becomes very clear. Okay, see here. Consider xy, 2xy, that is magnification in the x direction with scale factor sx equal to 2. This is the original object. Okay, if you give sx equal to 2 and sy is remains same. Okay, so height is remains same, but in x direction it doubles. Okay, so here 2 1 4 1. Okay, so it doubles means what? Here 4 1 8 1 double, 2 1 become, okay, in only x value. Okay, 2 become 4 and 4 become 8 here, and here 2 become 4. Okay, and 4 become here 8 here. Okay, 8 comma 2, and here it is 3. Okay, here it becomes 6. Okay, all x value become double and y value remains same. Okay, similarly assume sy is more than 1. Consider x comma y, x comma 2 into y. Okay, y get double means magnification in y direction with scale factor sy is equal to 2. Okay, the height get increase, doubles. Okay, so here all the y values. Okay, this is x value, y value, x value, y value. All y values get double. 1 become 2, 2 become 4, 3 become 6, 2 become 4, and 1 become 2. All y value get double. Okay, so sy is equal to 2. Object before scaling, object after scaling, sy is equal to 2. Okay, if it is consider xy, x dot sx dot comma y, where 0 less than sx equal to y2 less than 1, that is compression in x direction with scale factor sx equal to half. If sx is half, then see here x values are 2 here, 2 2 4 4 3 here, so it get half. 2 become 1, this 2 become 1, 4 become 2, and 3 become 1.5. Okay, like this. This object before scaling, object after scaling. Okay, similarly if you sy is equal to half, then this y value become half. Okay, 3 become 1.5, 2 become 1, like this, 1 become 0.5. Okay, if you give both sx equal to half and sy is equal to half, then both in x direction and y direction both get decrease. Clear, no? We'll take an example. Find the new coordinates of a triangle a 0, 0, b 1, 1, c 2, 5, 2. C value is 5, 2. After it has been magnified to twice its size. Second, reduced to half its size. Okay, first question is you have to magnify twice its size, double, and second question is reduce half its size. Okay, the triangle is given ABC. This is the triangle ABC. Okay. Okay, ABC, triangle ABC is given. Okay, A, B and C. So A value 00, B 11, A 00, B 11, then C X value 5 and Y value 2, 5 comma 2. Okay, so you have to magnify it to twice its size and reduce to half its size. First question, first we will magnify. Magnification and reduction can be achieved by uniform scaling of S units in both X and Y direction. If S is greater than 1, the scaling produces magnification. Okay, if S value, both X and S both are 1, more than 1, then scaling produces magnification, it enlarge. If S is less than 1, the result in reduction. If Sx and Sy is less than 1, okay, result in reduction. It reduces the size of the object. The transformation can be written x comma y comma 1 to x dot y comma 1. In matrix form, this becomes x comma y comma 1 into sx 0 0 0 sy 0 0 0 1 equal to s dot x dot y comma 1. We can represent a given triangle shown in figure A in matrix form using homogeneous coordinates of the vertices as, okay, A values were 00, A 00, B 11 and C 52. Okay, that is given. Okay, one simply you have to write. Then choosing S equal to 2. Double means what? Okay, 1 means uniform, 2 means double, half means, okay, half the size, 2 means double. Okay, choosing S equal to 2. Okay, both Sx and Sy, both are 2 means double. The matrix of scaling is S Sx comma Sy is equal to S 2 comma 2. Okay, Sx is 2, Sy also 2. Then write Sx and Sy here. Okay, so this is the equation. Okay, Sx Sy, write Sx value, Sy value here. Okay, the matrix. Okay, this is the matrix of scaling. 2 2 1. The new coordinates a dash b dash of the scaled triangle ABC can be found as, okay, a dash b dash c dash is equal to ABC dot r 2 comma 2. Okay, so this is given. Okay, these are the A position, B position and C position. One you have to write simply. Then this is the scaling matrix. Okay, 2 0 0 0 2 0 0 0 1. Okay, then you multiply 0 into 2, 0 plus 0 into 0 plus 1 into 0, you get 0. Okay, so like this you go on multiply, you get these values. Okay, so if you see here, okay, all it become double here, 1 become 2. Okay, then this only you have to see this one, only you have to see this one, only this column and this column. Okay, this one is common. Okay, one is common here, only first two columns you have to see. Okay, 0 doubles of 0 is 0 only, 1 become 2, this 1 become also 2, 5 become 10, 2 become 4, means what, it doubles. Okay, so thus A dash is equal to 00, B dash equal to 22 and C dash equal to 10 4. Okay, see here, this is doubles. Okay, A 00, B become what, 2 2. Okay, and C become 10, X value 10 and Y value is 4, 10 4. Clear, no? Okay, then second problem. Similarly here S is equal to half, means it's reduced. S equal to half, and the new coordinates are A dash equal to 00, B dash equal to half comma half. Okay, C dash is equal to 5 by 2 comma 1. The following figure B shows what effect of scaling with Sx Sy is equal to, this is 2 and Sx Sy is equal to half. Okay, if you instead of 2, if you use half or 0.5, okay, you get half here 0.5, here 5 become 2.5. okay, 2 become 1, okay, 1 become 0.5, like this. Okay, so finally you get this half. Okay, it reduces the size. Okay, object after scaling with Sx Sy equal to half. Clear, no? Okay. Thank you.